Hello, and welcome to this session on challenges and success stories. I am Dimitris Kolovos. I'm a professor of software engineering at the University of York, and I will be hosting this session. And we have four talks this afternoon, starting with Samana Khimji from the University of Warwick, and in particular the Warwick Manufacturing Group, where she's studying for an MSc in Smart Connected and Autonomous Vehicles. So Samana will talk to us about a model-driven approach for the concept Hyperloop pod, and I would like to invite Samana to start her presentation.
Thank you. Thank you for the introduction. So good afternoon. My name is Samana, and I am an MSc student of Smart Connected and Autonomous Vehicles at the Warwick Manufacturing Group. And today I will be presenting on a model-driven approach for the concept Hyperloop pod. So the research context for this project stems from the SpaceX student competition aimed to facilitate research around the future of autonomous, lightweight, and time-efficient public transport. A student-led team from the University of Warwick called Warwick Hyperloop participated in this competition and produced the data used for this project. And within this student team, I was actually the head of software and systems, introducing my team to the concepts behind systems modeling and control, and implementing some of the methodologies used in model-based systems engineering. Essentially, the Hyperloop pod is a magnetic levitation technology that is more compact, high speed, and lightweight compared to the technology that exists today. Currently, the pod stands at a technology readiness level of 6 because of the first real test track trial with humans in the loop over a 500-meter test track that occurred in 2020 to validate the safety of the pod. Unlike the automotive industry, this concept has not garnered enough literature in terms of its systems modeling and control. There is a lot of literature around the aerodynamics of the pod itself and how it travels within its vacuum tube. So this project was aimed at countering the knowledge gap by providing a more holistic model for the simulation of the Hyperloop pod using model-based systems engineering. So to begin with, the structure of this project was fundamentally laid out using the systems V model. On the left-hand side, we can see the system decomposition, and on the right-hand side, the system recomposition, which includes levels of hardware in the loop testing using the plant model and a prototype. However, this was beyond the scope of the project, and the focus was more to left shift the idea of the testing and the implementation of the model to the left-hand side of the systems V model. So to start off with, the business requirements were generated based on the SpaceX competition guidelines, which involved the high-speed requirement of 500 kilometers per hour and the duty cycle of a 24-second run that included an initialization phase and a phase for the pod to accelerate, and finally 3 to 4 seconds at the end for the pod to come to a hard brake. Moving on, the system requirements were formed based on the Warwick Hyperloop subteam requirements, which consisted of the powertrain, vehicle dynamics, and braking systems of the pod. And then further model requirements were decomposed and cascaded, and they were extracted from data sheets pertaining to the motor choice and requirements, and calculations on the braking system that were presented by the subteam. At each phase of the model development, white box model and the loop testing occurred to verify the system's functionality in accordance with the system's requirements. So the methodology of this project required an evaluation of 2 modeling techniques that would shape the progress and the direction of this project. On the left-hand side, there is an explanation of acausal modeling, and on the right-hand side, causal modeling. And both of these techniques are commonly found in modeling and simulation of systems, achieving very similar processes of how well the model developed within a simulation tool is able to achieve the desired output. However, they do so through 2 very contrasting processes. And the ability to evaluate which method was required was fundamental, because the objective was to model the behavior of the system from an investigative point of view and to understand the upper level physical topology of it. And so the figure on the left is a representation of what acausal modeling led me in terms of achieving a working model and the controller for the concept Hyperloop pod, in contrast to the right, a model which is actually taken from the literature review of my dissertation when I worked on it, that represents what my model would look if I focused on trying to establish all the signal flows between all the physical connections within the pod that I was modeling for each subsystem. So therefore, causal modeling was not the optimal choice because of the computational structure and algorithm, which would take away from a true representation of the physical systems and their behavior, and replace it with a web of signals flowing in every direction with an abstracted demonstration of the pod. So the final model of the pod consisted of a braking system with a fixed temperature coefficient, as seen on the top right-hand corner, a heat capacity, and a convection component to model the heat dissipation in the brakes in the surroundings, a model of the permanent magnetic synchronous motor, an inverter, and a gearing ratio to double the RPM motor speed to measure the system, to match the system requirements, and finally the vehicle dynamics of the pod and an animation of the road. Some of the constraints faced in the overall model included constant motor machine parameters that did not account for temperature dependencies within the environment, and ideal and maximum power constraints that did not meet the system temperature system requirements for the power. Moving on, the driver controller, it was a subsystem that consisted of a PI controller to modulate the values used to determine whether the system should accelerate, brake regeneratively, or additionally apply friction braking due to the regenerative capacity being maximized. And the use of the PI controller made it simpler to control the output characteristics of the pod because they were assumed to be simplified whilst disregarding any non-linearities within the system. And this ideal assumption eventually reduced the fidelity of the model in terms of how well it represented the dynamics and powertrain of the Hyperloop pod. But from an investigative point of view, the system still mimics the duty cycle and the speed requirements that were laid out at the start of the project. This is a trade-off, essentially, that can only be validated at the point of requirement generation at the beginning of the project. And it highlights the importance of traceability in modeling choices to a set of robust requirements that dictate how well the system functions compared to its desired outcome. So the chassis model consisted of a set of prismatic joints to model the lateral movement of the pod, springs and dampers, as well as a spherical joint to model the pitching of the pod during its duty cycle. The driven wheel of the pod is not modeled for due to a lack of literature that is present that is able to model an rather unconventional non-automotive configuration of a driven wheel within the Hyperloop pod. And if time permitted, experiments on COMSOL would have been carried out to create a physics-based model of the wheel and to then export it into the modeling environment in Daimoler to incorporate the driven wheel within the simulations of the pod. So having created this ideal model of the Hyperloop pod, model-in-the-loop testing was carried out through the estimation of PI parameters, and it was interesting to note that regardless of an increase in the controller gain, the system struggled to reach 500 kilometers per hour due to the power saturation that was present as a limitation of the model. And the high PI coefficients presented a jerky acceleration, as can be seen, and a sudden deceleration of almost 5 to 6 G within a second, which shows that this concept is not suitable for simulating passenger travel. And the constraints faced by the model were witnessed in the pod's longitudinal movement. To try and dampen the acceleration, of course, the PI values were modified through estimation, but also a drop test was conducted whereby the spring and damper parameters were configured to assess the steady state of the vehicle's ride height based on the pitching response of the vehicle. And the outcome of this test delivered spring and damper coefficients that would lead to less pitching of the pod during its duty cycle. And this in turn helped in reducing the transient response in the longitudinal movement of the pod. So in conclusion, the project was able to deliver a model of the pod. It was able to simulate its duty cycle and attempt to optimize its control method. However, despite the acausal modeling approach used to model the behavior of the subsystem relationships within the pod, the model failed to optimize its fidelity, and the results showcased a passenger-unfriendly response that would in turn cause severe injury and potential harm to individuals. The deceleration of the pod over time was hazardous, and this showed the limitations of the system and potentially a gap in the system requirements generated at the start and also designed for the target speeds that it was meant to travel at to activate hard braking of the pod within 3 to 4 seconds. The implications of this project carry gravity in the exploration of how model-driven engineering can be used to validate the safety of future autonomous high-speed public transportation, such as the Hyperloop pod. Despite the efforts to utilize model-based systems engineering in some aspect and ensure requirements traceability, the fidelity of the model was compromised due to a lack of literature that would potentially be used to benchmark the desired functionality of the pod and the layout of the control structure and the model. And from this, they raised 2 questions that would summarize the challenges into future research opportunities stemming from this project. Firstly, how can model-driven engineering be used to develop a means of testing the Hyperloop pod for the consequence of motion sickness and passenger safety because of high speeds and a conflict between the hearing and visual senses? And secondly, how can the optimization of modeling braking systems be achieved for safe passenger travel at decelerations greater than 2G, given the lack of literature available on Hyperloop braking systems? And this concludes the end of my talk. Thank you for your attention, and I'm now open to any questions.